welcome you all to our very first colloquium in fall 2020. It's a great pleasure for me to introduce our distinguished speaker, Professor Frank Timitz from Arizona State University. Frank got his PhD from UC Santa Cruz in '92. Frank has a broad spectrum of interests in many things in physics, and he has been leader in many areas of astrophysics, computational science, and also playing a very important leadership role in the American Astronomical Society. Just to mention a few things, he has made significant contributions to understanding stellar evolution, in particular nucleosynthesis, the chemical evolution of the whole universe. Also astrobiology, gamma ray astronomy, and so on. He has been developing the digital infrastructure for astrophysics astronomy. In particular, he has been taking care and educating people to use MISA. It stands for Modules for Experiments in Stellar Astrophysics. As we mentioned earlier, some of us here have attended some of his summer schools in beautiful California. He's also a world leader in developing online education. About 10 years ago, when he first visited us in person, giving a colloquium at dinner, he told us at the time, 10 years ago, he already had like 1,000 students in his online astronomy course. Later on, he developed that course into the world's largest 4-credit astronomy course, including over 10,000 students per year. It's so amazing. I don't know how much money he made and how much he got back from the university for that course. He was later put into the leadership position at the ASU to help the whole university to develop more online education. And he made important impacts there. Okay, he, as I mentioned, he's also a leader in the American Astronomical Society. He's currently serving as the senior lead editor of AAS journals. Also as an author and referee for APJ, I can personally testify that Frank has been doing a great job. He's extremely efficient, very careful, and he has been serving the community very well. Okay, well, because of his many important contributions, he has been recognized with several prestigious awards, and that's also one of the reasons we invited him, to visit us again. We tried to get him here last semester in person, but because of the situation, now we have the opportunity to communicate with him, listen to him online. So with that, I would like to pass this to Frank. Let's all welcome Frank. Frank, welcome.
Thank you, Baryonic. Welcome, everyone. Hi there to your first online colloquia of 2020. So I'm going to cover some new results on stellar neutrinos, and by new I mean like one of the papers I will be talking about was published 2 days ago. One of them came out in about 3 months ago, and one of them, although it was published 3 years ago, has found some new life, as we will see. So here's a list of my co-authors, grad students, postdocs, faculty, senior faculty, mostly theorists, some experimentalists, and of course, if I say anything silly, that's my fault. Okay, so I have about 38 slides, and they're broken down into 7 vignettes, and we will cover these 7 vignettes as we go through. Go ahead. Well, I don't see it here. Oh well. Go ahead and record your questions in the chat as we go along. I can't see the chat live here at the moment for whatever reason I don't understand. But anyway, we will cover your questions as we go. So I'll just sort of go. Okay. So as sort of as a warm up, crack. Public service announcement, Betelgeuse is still here. Has not exploded yet, if it will. So this particular shot was taken in December of 2019 when Betelgeuse was already visibly dimming to the eye. Normally, although Betelgeuse is variable, but normally it's about as bright as Rigel there, 0.2 visual magnitude. And so it's already noticeably dimmer to the human eye. And then it recovered, and then it went behind the sun. And it is just starting to come out behind the sun. And there are certain spacecraft that have the right angle that they can see it before Earth does. And the news reports that I heard the other day is that Betelgeuse is dimming again. So it'll be very interesting as Betelgeuse comes around. I mention this because I'm going to touch Betelgeuse a couple of times in this talk. Okay. So over the next decade, neutrino astronomy will probe the rich astrophysics of neutrino production in the sky. So in addition to the sun, so upper left, so things like from the Bohr-XENON collaboration, probing the internals of the sun, to the one supernova that we do have, 87A neutrinos, to most recently, blazar TXS telephone number, producing neutrinos in AGN from the IceCube collaboration. So these are the three cases we have, but there's a whole new generation of neutrino detectors coming online. These include Super-K with Gadolinium, SKJD, Juno, the Jiangmen Underground Neutrino Observatory. There's some dark energy experiment, XENON. And so they're ushering in this new generation that is going to start observing potentially what is currently undetected neutrinos. So the image there shows Juno. It's aiming to start taking data later this year. We have the Xeon dark matter project there on the right, and down below, we have one that is operating right now, and that is Super-K with Gadolinium. And so sort of shown on the illustration there on the left, the anti-neutrino comes in, it hits the proton, out comes a positron, it produces the Cherkanov radiation, and you get the Cherkanov cone, and that's the normal measurement. But also coming off that weak reaction is a neutron. And so by doping the water with gadolinium, you choose gadolinium because it has a very large thermal neutron cross-section. And so it sucks up that neutron, it puts the gadolinium in excited state, and when it decays down, off comes a gamma ray, and that is the new signal that comes out. And so you get an entirely new signal that boosts your ability to say what is going on with the neutrinos coming in. And we're going to touch that a couple of times. In fact, here it is on the first one. So this paper came out in November 2019, the sensitivity of Super-K with gadolinium to low energy antineutrinos from pre-supernova emission. Okay, and so I sort of highlight there in yellow what the punchline is, and that assuming a normal neutrino mass ordering, more than 200 events could be detected in the final 12 hours before core collapse for 15 to 25 solar mass stars at around 200 PC, which is representative of, for example, Alpha Ori or Betelgeuse. And they estimate that with their current sensitivity, a pre-supernova star could be detected with SKGD for up to about 600 parsecs away. It's like, wow, really? Okay, so one, we're going to hit Super-K with GD later on in this talk. But if they can detect a pre-supernova with up to 600 parsecs away, how many is that? Is that 10 candidates? Is that 100 candidates? Turns out to be about 31 candidates. So this is a map of the supernova candidates within about 0.6, 1 kiloparsec away. We are at the center of the circle there, and then going around, we've got rings at constant distance, 0.2 kpc, 0.4 kpc, 0.6. This is the celestial equator, and so the up and down arrows indicate above and below the plane. Betelgeuse is Alpha Ori, so this one is right here. It's about a 12 solar mass star. That's what the 12 means here, and it's about 0.22 parsecs away. Color coding here is hot, bright blue stars, OBA, or blue. Then we have the orangey stars, K, and then we have the red supergiants, M. And so these kind of a color coding and a map of what Super-K with GD could detect. That's kind of exciting. And so this paper just came out 2 days ago. We'll touch more on it later. But I just wanted to put a map when they say we can detect supernovae within a kiloparsec. How many is that? It's about 31. Okay, so let's explore some of these recent theoretical results that are going to provide three things. Number one, they're going to provide new targets for current, forthcoming, and future generations of neutrino detectors. They're going to provide new estimates for the stellar neutrino background signal. And they're going to provide new opportunities for nuclear experiments that can make a sizable difference in stellar evolution. So let's do a little background. Let's talk about neutrino production in stars. Where do neutrinos come from and what do they do? Okay. So as a reminder, stars radiate their energy by releasing photons from the stellar surface. So what you see with your eye, but they also release neutrinos from the stellar interior. On the right, the image is showing a cross-section of the sun. That is, the layers are drawn to scale. So we have, starting at the core, the radiative zone, the convection zone, the photosphere. The cross-section for neutrinos is of the order of 10 to the minus 44 centimeters squared. And this is some 20 orders of magnitude smaller than the Thomson cross-section, electron scattering, for photons, which is about 10 to the minus 24 centimeters squared. So the mean free path for neutrinos is large. It's about 4 times 10 to the 9 solar radii. And its time scale to reach the stellar surface is about 2 seconds. So that is shown also in the image on the right. You can see up here, this neutrino is going to come booming straight out of the stellar core. And on 2 to 3 second time scales, and the photon sort of does the Brownian motion walk, taking somewhere, depending on details, somewhere between 5,000 and 100,000, maybe even a million years before it produced as a gamma ray photon in the core, and when it comes out of the sun, it's a visible light photon. 1,600 visible light photons. Okay. So weak reactions produce neutrinos by thermal processes. This is one mechanism. And so the image here is showing as a function of density, as a function of temperature. So this is a Helmholtz free energy basis. The names of the various processes, these are all have counterparts in electromagnetics. And so you just replace the photons with the neutrinos and you get the corresponding process for neutrinos. So for example, pair production would be the production of E plus E minus and pair neutrino. You have an electron positron, which then goes to a neutrino antineutrino pair, generally electron neutrinos. The color coding here is the neutrino loss rate per gram per second. It's taken for a pure carbon composition, but it's fairly representative of other compositions as well. And so we have things like photoneutrino processes, we have recombination, we have Bremsstrahlung processes, bouncing off of nuclei, and then we have plasmon processes, which are collective oscillation modes that can turn into a new bar pair. Also shown here is green. This is sort of a typical track of, let's say, a 25 solar mass star. And once massive stars, excuse me, once massive stars get certainly to oxygen burning and carbon burning, they burn in a state of what is known as balanced power. So the energy that you generate from nuclear reactions is equal to the energy that you lose from neutrinos. And so they sort of follow this green curve, doing a balanced power burn in the final phases. So thermal processes is one way to produce neutrinos. Weak reactions can also produce them from beta processes. So you have electron captures, positron captures, beta minus decays, beta plus decays, and then you have de-excitations, which is a neutral current production of neutrino, antineutrino electrons. Okay, so those are the two ways that you produce neutrinos in the stellar core: thermal and beta processes. So now that we know what those are, now we'd like to do something about a star. So we're going to need a stellar evolution instrument to calculate what stars do with neutrinos, how they're produced, which ones matter the most, when do thermal matter, when are beta processes the most important. So we're going to need an instrument. And MESA is the tool that I'm going to use. So Bayon mentioned this, and I'll do a little bit on it here. So the MESA source code is a set of software modules for stellar astrophysics. It that can be used on their own or combined to solve the coupled equations governing 1D stellar evolution with an implicit finite volume scheme. The image here is what would be one row of the Jacobian matrix. So this is holding the derivative values. So you'll have pressure, temperature, luminosity, and you have your abundances here. And then you're taking the derivative of each of these quantities with respect to all the other quantities. And this is for the current cell. This would be for the cell deeper into the star. This would be for the cell further out. So it couples 3 cells. And you have various patterns in your Jacobian matrix depending on what's going on. So this is the coupling from to the previous, to the next cell. This is the coupling to the cell right before. Okay, but I don't want to talk about MESA, the source code in particular, in detail. This is my one slide on the source code itself. The MESA project is a bigger entity. And here are the current 15 or so active MESA developers who are helping develop MESA. Bill Paxton is the first author of MESA. He got it going. And MESA has had a really strong market penetration. There's currently 1,000 strong MESA users spread across the globe. Yeah, and it has had a good market penetration and is having an impact. So for example, the central, some of the bibliometrics of MESA. So here in the center is the citation count for MESA as a function of time. There are 5 different MESA papers. This is one of the innovations that we do. We don't have just one software paper. We put a new software paper out about every couple of years. That is an innovation in the community. And so this is going up and to the right. 2020 is promising to be a banner year. It's already September 1, and we've already exceeded the citations from 2019. So 2020 is going to be a banner year. Total citations to MESA currently is about 4,000, but a perhaps more important number is how valuable are those papers that use MESA. And so the citations to articles that use MESA for their science have a sum total of about 80,000 citations. And so if you divide these two numbers, 80,000 divided by the 4,000 to MESA directly, MESA is having an impact by about a factor of 20. I call it an impact radius, above and beyond the direct use of MESA itself. So it is having an impact into the larger science community. Okay, MESA is but one software instrument in an entire ecosystem that exists between, on the bottom here, laboratory astrophysics. So these are things that we do on Earth. So we have things like nuclear, NaCl, FRIB, but we also have phenomena like diamond anvil. So you take hydrogen, put it in the diamond anvil to get the thermodynamics of hydrogen under high pressure, applicable to things like Jupiter's Neptunes. And in the sky, then we have telescopes, things like SDSS, Hubble, and so on. And between the Earth and the sky is this ecosystem of software which interact with each other to maximize the science that comes out between this interaction of what happens on the ground and what happens in the sky. Okay. So now I've got a tool, and now I'm ready to make some stellar models with this tool and focus on neutrinos, the topic of this talk. So we go ahead, and the first thing we want to do, since we're going to be focusing on neutrinos, is we need a normalization. So normally you normalize things to the sun. So if you're doing photons, you normalize to the photon luminosity of the sun. And so we want to do the same thing for neutrinos. And so we construct what is called a MESA standard solar model. So this is a 1 solar mass model, the sun, and you compare various quantities. The one I want to highlight here is the neutrino flux. So these are the components of the observed neutrino flux. This is proton plus proton. This is from beryllium. This is from boron. This is from nitrogen. This is from oxygen. Here are the observed values from the Bohr-XENO collaboration as of 2011, and then updated a little bit. And then here are the numbers that come from MESA. These 2 different columns, we don't have to pay too much attention to what they are, but they're just different assumptions about what the composition of the sun is. Okay, And so PP, which is the main part of the signal, will be observed at 6.05, and depending on your composition, you get pretty close to that for PP. And then the same for beryllium, quite in bounds. Boron, very good. Only upper bounds observationally on neutrinos from nitrogen and oxygen, and we are well below those bounds. So overall, this is a pretty good fit to the neutrino fluxes coming from the sun. And for those, just to put a number in your head, the neutrino luminosity from the sun is about 2% of the photon luminosity. Okay, so that's the easy order of magnitude estimate number to keep in your head, that the luminosity of neutrinos is about 2% of the photon luminosity of the sun, or in terms of a particular value, around 10 to the 32 ergs per second. Okay. So having done a good one solar mass model, now let's take a look at a whole bunch of different masses. So the traditional diagram is called the Hertzsprung-Russell diagram. On the x-axis is the effective temperature of the star. So this is effectively its thermal radiator temperature, its black body temperature. And on the y-axis is the luminosity, how many ergs per second, what the power of the star is. And this is known as the Hertzsprung-Russell diagram. I've got color-coded here by different masses of stars. I'm not going to walk through the detailed evolution of the stars here, but we've got low-mass stars in green, high-mass stars in kind of a bluish color. And this is a classic. This has been done for 110 years. Okay, and one doesn't mess with a classic, or does one? What if you replace the y-axis, instead of having a photon luminosity, what if you put a neutrino luminosity on there? What would a neutrino HR diagram even look like? And that led to the production of the world's very first neutrino HR diagram. So this was published in April by Farag et al. 2020. And so on the left is the picture you just saw. This is photons, and on the right is a completely new look. Same stars, same everything, except now we're just going to look at the luminosity of the neutrinos on the y-axis. Again, you've got low mass stars in green, you've got high mass stars in blue, and I've labeled off a particular number of features in the evolution of stars. So this is the zero age main sequence. So this is where stars are happily burning hydrogen quiescently in their cores. Then they eventually run out of gas in the middle, and so they peel off, go toward a cooler surface temperature. And then depending on the mass, they will have different phenomena. So down here in the low mass stars like the sun, so this is the sun right here, the sun will peel off, it will go through some helium flashes, producing some neutrino bursts. That's why it's spiky, they're called flashes. So these spikes are real, this is not some numerical silliness. Okay, then they ignite helium. Eventually they run out of helium in the core. They undergo some thermal pulses, which produces some pretty large neutrino fluxes. We'll get to that. And eventually the outer layers blow off and you transition across to a proto-planetary nebula, and you come down to the white dwarfs. High mass stars do something a little different. They basically go from helium and then start burning helium ignition and carbon ignition, oxygen, silicon, and then the onset of core collapse. So this is the pre-supernova neutrino signal for massive stars. And we'll cover that in a little more detail here in a minute. Okay, this is the world's first neutrino HR diagram. How cool. So let me get to a question I asked earlier. When do photons dominate? When do neutrinos dominate? And so I've split this up into low mass stars on the left, high mass stars on the right. And colored green means that the neutrinos are dominating photons by a factor of 10. Okay, so just looking at the green, this is when neutrinos dominate. And then on the brown is when photons dominate neutrinos by more than a factor of 10. And so down here at the lower parts is when photons dominate. And in general, not always, but in general, neutrinos tend to dominate at the end of a star's life. Okay, otherwise photons carry the bulk of the energy loss of the star. And we talked about thermal processes, production of neutrinos, and beta weak reaction, beta processes producing neutrinos. Which one dominates where? And the general answer is that neutrinos from beta processes tend to dominate whenever hydrogen or helium can burn. If there is no hydrogen or helium, then in general, thermal processes will dominate the emission. And so again, color-coded here, green is when thermal dominates over reactions, and then in brown is when reactions dominate over thermal by a factor of 10, and blue's kind of in the middle realm. So massive stars are generally dominated by thermal until they get to the very onset of core collapse, when thermal and reactions are within a factor of 10 of one another. So both thermal and beta processes are contributing roughly equally, order of magnitude-ish, at the onset of core collapse. Okay, cool. So there we go. So let's dig in a little bit on those massive stars as they approach core collapse. I'm going to probe the evolution of pre-supernova models. So I want to put this in context, a little bit larger context for you before we get into some details. This is a neutrino light curve. So on the x-axis here is the time, and on the y-axis is the luminosity, a light curve. How does the luminosity vary as a function of time? Time here is going to be measured from core collapse. So 0 here means core collapse of the central object. And then time goes out positively this way. Things that happen before 0, this is the pre-supernova stars, and these happen before 0. You can see the magnitude of the nu bar E, neutrino luminosity in ergs per second from 10 to the 47 up to 10 to the 53. Okay? And so what we are going to talk about here is the pre-supernova stage. And we'll talk about why they give you an early warning. So instead of being an afterthought, they can actually lead the field by telling the electromagnetic and the gravitational wave communities, hey, there's a supernova coming, get ready. And not only that, not only can you say get ready, but you might be also be able to say, get ready, where should I look? You should look over there. Okay, and so we're going to talk about that, how you can use neutrino detectors as pointers to tell. You're also going to learn some stuff about progenitor physics. Then the main event happens. Then you have the bounce, and so you have accretion of material falling onto the proto-neutron star. So the new physics that you get out of here is flavor mixing, neutronization. You can also get the supernova distance during the accretion phase, and you'll be able to probe multidimensional effects. Then the neutron star begins to cool. First, you have the mantle cools and the core cools. This is going to tell you about the nuclear equation of state, the energy loss rates, the proto-neutron star radius. So we'll tell you about the diffusion time of neutrinos in a very dense environment, and it will also allow you to probe beyond standard model physics. Eventually, it starts to thin out. It starts to become optically thin to neutrinos. So you have the neutrinosphere recession, and then fallback. Once that clears out, not everything that bounced off is going to achieve escape velocity. Some of it is going to fall back down. That's why it's called fall back, because it was pushed out, didn't quite get to escape velocity, comes back down. And this late time of the neutrino light curve is going to be able to tell you what was actually formed, a neutron star or a black hole, the time to transparency, when does it become optically thin, integrated energy losses, and again, you're going to be able to probe beyond standard model physics in the late time phases of a neutrino light curve. Okay, so we're focusing on the pre-stuff. Everybody, hey, get ready, get your telescopes and gravitational wave detectors together. Okay, so this is the march to core collapse. This is a detailed shot of what you saw in that neutrino HR diagram. So this is the time to core collapse on the x-axis. So 0 or minus infinity on this one corresponds to the core collapse event itself. This is the time before core collapse. So 100 seconds, 10 seconds, so on. And this is the luminosity as measured in number per second. So it's a number count. This is the oxygen shell. Things start getting really interesting by the time you get into silicon burning. The different colored curves here correspond to what we've been talking about. This is beta processes versus thermal processes. And in general, in silicon, as you start approaching the onset of core collapse, they all contribute, and they're generally within about a factor of 10 of each other, which is what we saw on that colored diagram. Okay, so they start getting pretty large as you get up tens of hours beforehand, before the main event. And this is another take on beta processes. So this is in the Helmholtz free energy basis. This is the central density of the star. This is the temperature, the central temperature. And this is the track that the white is the track that a star follows. All of these zigzags are real. In general, if I drew a line here, stars generally evolve along a radiation adiabat. So T cubed over rho is approximately constant. And every jig here to the left generally means that you've got an electron degenerate fuel that you have ignited. And so this is silicon burning. This is the onset of silicon burning. You can see the jog left. That's very characteristic of a silicon burn. Same thing here. You get a jog to the left at the onset of oxygen burning. I've marked here in triangles various time points starting from about 2 hours to a few hundredths of a second before core collapse. And then we did a very detailed analysis of what are the reactions, what are the isotopes that matter. They're putting out most of the neutrinos or antineutrinos, as the case may be. And so we break it down. And so this gives targets to the nuclear experimental, particularly the weak reaction community, and the theorists as well. Can't forget the theorists. On improving or measuring these weak reactions, because they matter in the last few hours of the star's life, which are going to be measurable here. Okay. So in Patent 8L a few years ago, 2017 now, we did these calculations and we took a look at the pre-supernova fluxes at 1 kiloparsec. And so the baseline takeaway that I want you to remember is, number one, that at 1 kiloparsec, the neutrino flux is as strong as they are for solar neutrinos. And we certainly measure solar neutrinos. And things that might be background, it might be contaminants, such as the Earth, in fact, produces neutrinos. These are GM neutrinos. We also have reactors, nuclear reactors on Earth. These also produce background neutrinos, and they are lower than what the signal is going to be by several orders of magnitude. So for example, here on the left, this is a spectrum. This is the energy as a function of flux at Earth at 1 kiloparsec. This is for a 30 mass star, assuming a normal hierarchy, neutrino hierarchy. And so here is the signal we expect as 2 hours gets closer and closer and closer to core collapse. The flux gets larger and larger. The gray here is the solar neutrino fluxes. And so you can see that the pre-supernova flux is about of order what you get from the sun, should be observable. On the other side here, on the right, this is the same 30 mass star, but this is the new E bar flux, normal hierarchy. And the point here is that the reactor and geo neutrinos are much lower by a couple orders of magnitude from the signal. So they're not going to be confused with reactors of the Earth. Okay. So we could have stopped there and just said 1 kpc, and you know, it's obvious how to scale, but we decided not to do that. And I think that was an interesting thing to do, is we actually went and took the results and applied them to a very specific object. And what we applied them to was Betelgeuse. See, Betelgeuse coming back in this talk. So a prime example is the red supergiant Betelgeuse, Alpha Orionis. And we find that for 200 parsecs, a pre-supernova signal would be practically background free. You just saw that in the previous picture. In energy windows that are realistic for detection for several hours, and in the window of observability can extend up to 10 hours before core collapse. Okay. Well, this was interesting and fun. And it got picked up by Super-K with Gadolinium. And so they did some comparisons of our models and other people's models. So on the y-axis here is the inverse beta decay. This is IBD, inverse beta decay, as a function of time. And so even 10 hours before core collapse, they're predicting to pick up a few hundred events. Okay, and then down here is the inverse beta decay. This is the spectrum of the positron that you expect to get. And so I just found it so humorous, I guess, that in their paper, the Simpson et al., they said a pre-supernova could be provided to the gravitational wave and electromagnetic communities. I just find the could there kind of amazing, because if you got 200 events, you would most certainly tell the electromagnetic and gravitational wave communities that something's coming, get ready. So that would be interesting. So now that they've detected, or let's say they will hopefully detect something, right? So the detectors go off and they're giving an alert that a core collapse event within 1 kiloparsec is coming. So where do you look? How do you identify the progenitor before the big light show comes? Because you have to point your telescope somewhere, and so it'd be nice to identify that progenitor. Okay, and so the essence of it is given in this plot right here. The neutrino, antineutrino electron comes in, smacks the proton inside super-K with GD, let's say. Off comes the positron. Eventually, the positron meets an electron, and they could do E plus E minus. You can measure that. You can find where that happens, so you know where this is. Also comes out is the neutron. The neutron comes out of that weak reaction. It has to thermalize. This is the thermalization here as it's bouncing around thermalizing, and eventually it will find gadolinium, where it will be absorbed. That gadolinium will then excite and de-excite and then put out a gamma ray. This was the new signal that we were talking about for super-K with GD. And so you can draw a vector between where the E plus E minus was detected, where the gamma ray was emitted, and that gives you a directionality. And it is this directionality that is going to allow you to determine where the neutrino came from. In other words, point back to the progenitor. Okay. So we do this in this paper that just came out 2 days ago. And so if you do a standard liquid scintillator, okay, we find that you can localize the pre-supernova to about 70 degrees after just 100 detections. Okay. Now 70 degrees is actually pretty good. That's eliminating half the sky. Well, you don't have to look over there, it's at least over here. And as you get more and more detections, that percentage will increase. So what is on the x-axis here is the number of detections, and then this is the angle that you can observe the supernova in. Next generation neutrino detectors, you might want to throw a little lithium in your liquid scintillator because this will significantly improve the sensitivity. And if you had a lithium doped liquid scintillator, then instead of being 70 degrees, you could nail it down to 15 degrees after just 100 detections. So current and hopefully near future, 70 to 15, pretty good. Okay, and just to give you an example, there are other massive stars, as we saw in that plot, besides Betelgeuse. So let's take a look at Antares. This is the brightest star in Scorpion, in the Scorpius. And so this is a Molenweed projection of the entire night sky. The green line here is the galactic plane, and so it's not flat because we're in a Molenweed projection. So it's green. The dots here are the 31 supernova candidates that we saw earlier in this talk. And then if you got a signal at 4 hours before the main event, these are how much of the sky you could eliminate. So at the 95% level, this is the 70 degree mark, you're eliminating about half the sky. So everything up here, you don't have to look at. You only have to look down here. If you had lithium doped liquid scintillators, then the contours start getting much smaller. And at the 95% confidence level, you're eliminating all but about 4 hours beforehand. So this is really telling people where to look on the sky. 1 hour before core collapse, the air contours shrink quite a bit. And by the time you get down for Antares, which is a 15 solar mass star at about 0.2 parsec, about 2 minutes before core collapse, you can pretty much nail down which star is going to be happening. And even if you don't nail it down to 1, that's perfectly fine. If you nail it down to 3 or 4 in a given region, let's say it was over here, or here's Betelgeuse, that's Betelgeuse right here in the red square. Even if you just nailed it down here, you're eliminating most of the sky, and you're telling people where to look, and that will help the electromagnetic and gravitational wave communities a lot. And it would be very exciting too. Okay, Supernova are the main game in town with regard to stellar neutrinos, but they're not everything. There are low mass stars, there are the sun, so we don't want to forget about them. So as we saw in this neutrino diagram, you've got some interesting spikes here, right? Where these spikes from low mass stars begin to rival what you would get from a massive star during carbon burning, for example, as they go through what are called the thermal pulses. And so this is very strong hydrogen helium burning on the surfaces of stars that will in time become white dwarfs. And so we go through the analysis and you know, for example, you can reach luminosities of 10 to the 19 or 10 to the 9 during the thermal pulses. So the advantage, although the luminosity is a lot less, there's also a lot more low mass stars. And so you might have a much better chance of getting something from a low mass star than you would for the much rarer high mass stars. Unfortunately, there are no good nearby targets for detecting either helium flashes or thermal pulses from low mass stars. On this plot here is as a function of time. So 0 is now. So this is 100,000 years in the future. This is 100,000 years on the past. This is the heliocentric distance of the nearest stars to Earth, to the sun. So in the current epoch, Alpha Cen AB Proxima is currently the closest star to the sun. It's going to get even a little closer in about 25,000 years. It will be even closer than it is now, so it's moving toward us. Here is Sirius. This is a white dwarf. And so the dots here are simply marking the point of closest distance to the sun. And then their orbital trajectory through the galaxy is shown as the colored lines, okay? And so unfortunately, none of them get particularly close enough. They also have very long lifetimes. So low mass stars are going to take a little bit more time or a significantly better sensitivity in your neutrino detectors to pick them up, okay? So it's now 2:44. I've been talking for, well, 2:44 my time. It's 4:44 p.m. your time. And so it's near the end of the day. And so after absorbing these 37 slides, you go off afterward. Perhaps it is time for everyone to share a neutrino cocktail, virtual or otherwise. And with that, I thank you for your time, and I thank you for your attention.
Oh, thank you, Frank. I have the first question. Who made this picture? Very nice.
This picture right here?
Yes.
I should attribute it, and I know the attribution. It's bad of me not to put it on the slide, but yeah. Why, you want one? You want a neutrino cocktail?
Yeah.
Would you prefer the Would you prefer the yellow, the orange, or the green?
Well, I like to have each one. Have a sample. Okay. Can you look at the chat? There are already 5 questions. Maybe you can quickly go through them.
Sure, we can take questions. Let's see. Now I see the chat window. Okay. Okay. Can you tell more about flavor mixing? Can you explain more about flavor mixing neutronization as it refers to possibly detecting dark matter? Not sure I have a whole lot to say about that. From the neutrino light curve, you can tell, if we've got detectors up, you can tell about the flavor mixing in dense material, right? So this is, a neutron star material, so the baryon density is quite high. And I would imagine if you had information there that you could use it to constrain dark matter signals that may be coming in much less dense environments. Unless you think there's a lot of dark matter in neutron stars or proto-neutron stars, then you could say something.
Okay, thank you. There's another question that came
in. Considering a superchandra white dwarf, which is near to collapse, superchandra, okay. Would it be possible to extract a signature of it using neutrinos. Yes, there will be, depending on exactly what happens to do that super neutrino, but yeah, it will put out a neutrino, either because the superchandra is going to explode, in which case all of the neutrino signals are going to be coming from burning nuclear reactions, or if it happens to do an accretion-induced collapse and it goes to a neutron star, then pretty much the same game that we were just talking about for massive stars holds in that case. You're forming a compact object. You just don't have 10, 15, 20 solar masses on top of it. You've got, you know, maybe one solar mass or half a solar mass or less of envelope on top of it. So a lot of the same lessons probably apply to white dwarfs. I can't recall right at the moment anybody doing that calculation. But it'd be well worthwhile doing, right? Because there's a whole new generation of neutrino detectors coming on. So now is the time to lay down your predictions. Get it out there.
Okay.
So, you know,
I have a question.
I kind of, I'll make a slight philosophical remark here. Right? So people were producing gravitational wave signals, you know, 30 years ago. When Joe Weber's cylinders perhaps were shaking. And so people would always throw, you know, gravitational waves, you're never going to measure those, right, 30 years ago. Well, here we are, and not only were we measuring them, but we're finding out some fantastic properties about compact objects in the galaxy. So it only took 30, 40 years to get to the point where we could detect them. And I think probably neutrinos are probably in that same game with respect to neutrino astronomy. It's a good time to make your predictions now, because when that comes, maybe next week if Betelgeuse goes, might be 10 years, might be 30 years. So I think there's some similarities between gravitational waves 20, 30 years ago and where we are with neutrino astronomy today. So now's a good time to make your predictions, even for superchandras. Go.
Okay, Carlos?
Frank, I have a few questions. In fact, maybe only two. Your MESA code, it is one dimension, you said?
It's spherically symmetric, yes.
So there are claims, I'm sorry because I do not play this physics. There are claims that three-dimensional calculations are essential because of Rayleigh stabilities and other convection phenomena, for example, that use some tricks in one-dimensional calculations, but they are not enough. So you have talked about core collapse supernova. So I saw all these calculated with your MESA code.
Mm-hmm.
Yes?
Yes.
And so what you have to say about these claims that you really need a 3D code?
I think people who make that claim are advocates of 3D. I think there are limits to those statements. There are cases when 3D matters and there are cases when it doesn't.
Yeah.
The other thing about 3D calculations is you may get a couple in per year because they take an enormous amount of resources. So you cannot do parameter studies, right? You're going to take your best shots at it. In general, they put all of the compute resources into spatial resolution. So if you want to learn something about isotopes, they don't do it. Okay?
Mm-hmm. Mm-hmm.
So I think that they are complementary tools. I think there are a lot of things that one can still learn about events from one-dimensional models and subgrid models of complicated phenomena like convection. And there are cases when 3D models do matter.
Mm-hmm.
So to me, both tools are useful. I don't think it's one or the other. I would not piss off on one dimension just because it's one dimension.
Right. Yeah, I had another question, which is your Hertzsprung-Russell neutrino diagram. Do you have a hope it could become observational? Because right now it's purely theoretical.
Well, that was the point of this talk, right? So we're getting to the point where Super-K
Mm-hmm.
is going to be able to start probing, assuming we get one, the upper ranges of that Hertzsprung-Russell diagram.
Mm-hmm.
So I would claim that they are on the cusp
Mm-hmm.
of being observable.
Mm-hmm.
We're going to have to drop the sensitivity of the neutrino detectors by another couple of order of magnitude as we start pushing down from the top on that neutrino Hertzsprung-Russell diagram. And at that point, then yes, it starts becoming an observable.
Yeah. Okay. My last question is the neutrino-lepton interactions, and when they involve only electrons and photons. So they are well known. I think QED provides a good handle of those cross sections. But when it involves nuclei, then it's not so simple, right? So there is a lot of people there are a lot of people working on that, right? So yes, and as I understood from your talk, they are also important processes which can contribute to a lot of neutrinos or modify their spectra, right?
Oh, absolutely, certainly, certainly. Yeah, that's a very active field. So just to go back to your first question, so you will calculate something in QCD, or you'll do some ab initio Green's function Monte Carlo calculation on this stuff, and you'll get a result, and you'd like to know what the impact of that is. Well, you could wait around several years until somebody gets around to doing a 3D calculation, or you could put it in a 1D model and at least get a 0th order effect of what is the impact of this new calculation or this new measurement. And then, and usually only then, if it looks like it's an interesting effect, might you attract the people who do 3D calculations to put it into their 3D codes and do 1 or 2 runs with it.
Okay, thank you.
Sure, thank you, Carlos.
Frank, I have a question. When you were talking about the how to tell in which direction you should look for a progenitor, or before supernova explosion happens, you have a diagram showing an antineutrino collide with a proton, becomes emit an electron, and then the neutron will collide with something else, give you a photon. Are you using the photon to try to solve in which direction? Is the photon you are detecting? Which messenger, which particle you finally detect to tell in which direction you want to look?
Oops, rat. Okay, I have to put it in play mode here. Now I can share. This diagram?
Right. So my question is really, because your neutron will collide with so many other particles around, don't they lose the information afterwards? I mean, your photon will come out, right? But before it comes out, both the neutron and electron, they will collide with so many other particles. At the end, the particle coming out will forget about where they come, right? Because in between, you collide.
Yeah, I mean, it does a thermalization, random walk here before it finds the gadolinium at thermal energies to absorb. Yes.
But how could they tell the direction where the neutrino is coming?
Well, this is described in the paper how you do this, and it's really a statistical argument. You're totally right on what you're saying. If there was only one, there would be some uncertainty. But by the time you get to 200, 400, you can start doing a statistical analysis and beat that down, because they will presumably all came from the same event.
Okay.
And so this is described in detail in the paper that came out.
Okay. So it will depend on the density of the interstellar medium, or the environment, right?
So what we're talking about here is in the neutrino detector.
Oh, okay. Sorry. Yeah.
This is in the neutrino detector.
Okay. Then I understand.
Okay. Right. Because this is your Cherkanov cone coming out. This is E plus E minus. This is, instead of saying neutron here, this red, this is the gadolinium atom.
Okay.
The neutron is absorbed on gadolinium here. And so this is all taking place inside the detector. Okay.
Now I understand.
Okay.
Do we have any other questions from other people here in attending this colloquium? Any other questions? You can just speak out and ask directly.
I just wanted to ask, what is neutronization?
Okay, neutronization is when you start forcing, well, you start undergoing weak reactions and all the protons turn to neutrons.
Okay, that seemed simple. Thank you.
That's the simple answer. Neutronization is when material starts becoming neutron rich, and there can be a variety of reasons for that, right? You can make the density so high that you start pushing electrons onto protons, and so they become neutrons.
Okay.
Yep.
Thank you for the explanation.
Sure. That's the
Okay.
simple.
Any other question from the student here? Any questions? Well, if no, let's thank Frank again. Thank you, Frank.
Thank
Have a
you.
great day.
I will. Thank you, everyone. Stay safe. Go enjoy
Stay
your
safe.
neutrino cocktails.
Thank
All the
you.
best.
Great.
Bye-bye.
Bye-bye.